Okay guys, as promised, I just wanted to finish up example 6 through this video so that you guys can tackle the homework that I've assigned. The goal is to try to come up with one of these schematics. That's basically a diagram that indicates the position of the particle throughout its journey. This is another one where it's going to be valid for all values of t greater than 0. And what you're going to indicate is places where it starts, obviously at t equals 0, and then any places along the way where it changes from speeding up to slowing down, or if it changes directions. Obviously this one changed, the example 5 changed at t equals 1 from slowing down to speeding up, but it also changed directions at that point. And once you have the schematic drawn, you can do things like compute the total distance traveled over a certain period of time, because you can see literally the path that the thing takes. So that's our goal. So I've written our position function here, and obviously you can see it's a cubic. So the first thing we want to do is get the velocity function and the acceleration function, and then we're going to look for the zeros or the critical numbers of both of those. This thing, the only critical numbers will be zeros because it's a polynomial, so it's not going to be places where it's undefined or undefined, I guess. So let's take the derivative, 3t squared minus 12t plus 9. That looks like it's going to be pretty convenient. I'm going to leave myself a little room so I can factor that and get the zeros before I go on and get the acceleration function, which is 6t minus 12. So back up to our velocity function, if we were setting this thing equal to 0, it looks like I would take a 3 out and get t squared minus 4t plus 3, which of course further factors to t minus 3 and t minus 1. That actually looks a little sketchy. Let's make that better there, minus 1. Set that equal to 0, and we have our critical numbers at t equals 3, t equals 1. And as far as our acceleration function goes, if that guy is going to be 0, it's going to be t equals 2. So very rigged formula here. So we have nice critical numbers for the velocity function and the acceleration function. So I think what we're going to do now is create one of those sign charts for both the acceleration and the velocity. Okay, so I've taken the liberty of going ahead and making a sign chart for the velocity function and for the acceleration function. And you can tell our velocity function here is 3, t minus 3, t minus 1. So by testing numbers between 0 and 1, like a half, that would make this factor negative and this factor negative, and the product of two negatives is positive. And between 1 and 3, take a number like 2. This factor would still be negative. 2 minus 3 would be negative, but 2 minus 1 would be positive. So a negative times a positive is negative, so it's going to be negative. The velocity is going to be negative through there. And then lastly, to the right of 3, both of these factors would be positive, and of course you're positive straight on out the rest of the way. So we can do the same thing for our acceleration function now, filling in this chart. Between 0 and 2, looking at our acceleration function, if you use a number like 1, 6 times 1 minus 12 would be negative. So we are going to be moving with negative acceleration here. And then once we get beyond 2, a number anywhere to the right of 2 would make that acceleration function positive. So I'm just going to put pluses, showing that we have positive acceleration for the rest of the way out there. What we now get from this information is, for example, our velocity function. Where velocity is positive, our object's moving to the right. Velocity is negative, it's moving to the left. Velocity is positive, it's moving back to the right. So this thing is going to start out and move to the right, stop, turn around, move to the left, and at t equals 3, it's going to stop and turn around and move back to the right. Meanwhile, with our acceleration and velocity kind of looking at them together, it might be interesting to go ahead and mark time equals 1 and time equals 3 here, so that we can start to see these regions where the velocity and acceleration have the same sign, for example, as they do between 1 second and 2 seconds. I guess I should go ahead and put a 2 up here as well. You can see that between 1 and 2 seconds, both velocity and acceleration are negative. And again, between 3 seconds and beyond to the right and 3 seconds and beyond to the right, both signs are positive. So those are areas here and here where the particle is going to be speeding up. And then we talked, of course, about when velocity and acceleration have opposite signs, that's when the particle is going to be slowing down. So between 0 and 1 and between 2 and 3. pretty much ready to go with drawing a schematic for this thing, and then we'll be done the problem. We can answer any question that could come across. So before we go and make our schematic, I thought I would take the time to figure out the position of the particle at all of our different critical numbers, both for the first derivative and second derivative. So I did s of 0, just plugging things into the position function to get our positions. So this thing starts at position equal to 1. After 1 second, it's at 5. After 2 seconds, it's at 3. 3 seconds, it's at 1. And I went ahead and just did one more. I thought, what the heck. After 4 seconds, I just got a sense and plugged in 4, and I got 5 here. Now, I'll probably finish this thing and realize I made an arithmetic mistake somewhere because I did that pretty quickly, but I think those numbers are right. So now we're good to make a schematic. So what we have is essentially a number line here. I used values that I saw come up in our work with the different positions that we had at different times, 0, 1, 2, 3, and 4 seconds. So this number line represents position of the particle as it goes through its journey. So the first thing we have to do is identify where the particle is when it starts. So we can see that s of 0 is 1, which means at time 0, the particle is at position 1. Now, from our schematic, or from our sign charts up here, we see that for the first second, from 0 to 1 seconds, the velocity is positive. And what that means is that the particle is going to be moving to the right. Now, it's going to be doing that for the first second. So if we know where we are after 1 second, we can figure out how far this particle moves to the right before it stops at 1 second when the velocity is 0. So if you look at s of 1 is 5, that means that after 1 second, this thing is all the way over here at position 5. So I'm going to put a dot here to show that our object went all the way over to there. Actually, I think what I'll do is show that it's going to turn around there at position 5. Actually, that's a pretty lousy line, so I'm going to make that go again. So we're going to come around here and turn around when our object gets to position 5 right here after 1 second. And again, we can see that because we know that that's happening because the object moves to the right because the velocity is positive for 1 second. And we know at 1 second the object is at position 5. So we can go ahead and add to our drawing here by just showing that it's moving in this direction. So we put these little arrowheads on here. We can say that this is t equals 0. It's our starting point. We can put t equals 1 here to identify that. And we can see, of course, that it does turn around at 1 second because the velocity goes from positive to negative. So we can go back to this thing and say, okay, now we're going to start to turn around and come back to the left. But it would be good to check in and see, where are we going to be at different times. And we know that at 2 seconds we're at position 3. So I could go ahead and put in a dot here at position 3 and know that when time equals 2 seconds, that's where we're going to be. Now, it's important to realize that, yes, we're moving to the left, as you can see by those arrowheads, between t equals 1 here and t equals 2 here, and that's shown up here by our velocity being negative. Now notice, I didn't start to make this thing make a turnaround like I did here at t equals 1, because on both sides of time equaling 2 seconds, the velocity is still negative. The particle's not going to turn around again until the velocity switches from negative to positive, which is going to be after 3 seconds, and you can see at 3 seconds we're back to position 1. So I'm going to go ahead and put a dot here at position 1, which is going to occur at 3 seconds. So I can continue on my way and show that we're turning around there after 3 seconds, showing that the position at 3 seconds is at position 1. And hopefully, if I look at my chart, it's going to turn around and head back out that way. And sure enough, after 3 seconds, our velocity is back to being positive, which means we're moving out to the right. So I can continue my arrow and shoot out that way. And again, all these arrowheads, we're going left here, left here, left here, left here, left here, and then right, 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 and so forth. Now, we've captured the object's motion. I guess I could finish it off here because we do know that at 4 seconds the thing is back to position 5. So I could go like this and say at 4 seconds, here we are back to position 5. And I can go ahead and put t equals 4 there. And this thing looks like it's going to continue to move to the right because for all times greater than 3 seconds, the velocity is going to be positive. Now, the only thing we don't have accounted for on our schematic is when we're speeding up and when we're slowing down. So for this first second of the journey, we have positive velocity, which means we're moving to the right, as the arrowheads show, but the acceleration is negative. So that means we have opposite signs, and we learned today in class that means it's slowing down. So in red here, we're going to be slowing down for this entire first second from right here at t equals 0 at position 1 to t equals 1 second at position 5. Now, the particle changes direction because the velocity goes from positive to negative, and it kind of makes sense that it went from a dead stop, velocity was 0, turns and goes to the left, and at that time the acceleration is also negative. So that means this thing is going to be turning around and speeding up because our velocity and our acceleration have the same sign. So it's going to be speeding up to the left. So in blue, I'm going to write speeding up, which we know is true between t equals 1 and t equals 2. So I'll kind of highlight this part of the journey in red when it's slowing down. And now we move to the time between t equals 2 and t equals 3. And we're still moving to the left, our velocity is negative, but our acceleration is positive now. And because those two have opposite signs, that means we're going to be slowing down. So for this part of the journey between t equals 2 and t equals 3, we are slowing down, which kind of makes sense because before we can be stopped, as we are at 3 seconds, we must have been slowing down. And now for the last part of the journey, from 3 seconds onward, our velocity is positive, which means we're moving to the right, and our acceleration is positive, and because those two things are the same sign, as we move off here to the right, we are speeding up. And that pretty much wraps up our schematic. So this is what the object would look like. It starts here at t equals 0, and it's got some motion when we, the velocity, for example, at t equals 1, would be about 3 units per second. If you get v of 1, it would be 3 units per second. So this thing is already moving when we join the progress right here at t equals 0. So this thing's moving and it's slowing down, slowing down, slowing down until it comes to a stop and turns around and comes back, speeding up. Now it's slowing down again, and it slows down. Then it's going to take off and boom out to the right like that. Now, it's important to realize the object isn't doing this slalom course like this. The object is simply moving back and forth. So it comes over here, stops at 5, comes back, stops at 1, and then comes back and goes out to the end. Well, there you go, guys. There's a schematic for a typical polynomial function. Take care.